Hi, this question here is about Euler's equation for the fluid or an element of a fluid. Starting from the Euler equation for a fluid of constant density ρ and with a volumetric external force, potential force given by minus ρ times the gradient of phi, where phi is a scalar potential. You should show that ddt of this integral integrated on the volume, and this is the volume, plus the integral um, of this boundary of the volume, so that's a surface area, it's equal to 0. So that's not, it's missing here, it is equal to 0. All right, so it's to prove that that quantity h is whole v squared over 2 plus p, which is the pressure, and plus whole times phi, yeah. And this quantity h can be called the Bernoulli constant or Bernoulli quantity, because it has to do with the Bernoulli's equation for a fluid. And it's by that formula where it's written there, summand is equal to 0. It is transportable energy. And the question is basically just asking to prove that this identity is valid. Right, so starting from the Euler's equation for the fluid, you need to remember what's the Euler's equation is about. It's about force and acceleration for an element of the fluid, particularly for a barometric flow, so a barotropic flow, which is a flow in which the density depends on the pressure. So that's barotropic flow. So when the density is constant, as the question said, constant density ρ. Constant density is a particular case of barotropic flow. So you can start from this equation, which is the Euler's equation for a barotropic flow. So that means, as you can see, the ρ depends on the pressure. So it's a bit general, but then you specialize to what you want. So what you want is to use that the constant is the density is constant. All right, so that's the derivative of the velocity, and phi is the scalar field, and p is the pressure, and ρ is the density. But in particular, as the question said, this ρ is constant. So because of that, we need to change, take in particular that this ρ is a constant. So therefore, this integral of dp is basically just p, right? This is written here, just p. The ρ is a constant, so goes outside of the integral. Here, I'm just mentioning that this quantity, the curve of v, is called the vorticity, and you know that it has other kind of applications for vortex theory. But here, I'm just mentioning to remember what is the meaning of that thing. Here is the vorticity of the curve of the velocity field v. All right, so then you have that. So you want to prove that identity, that ddt of something plus this integral on the boundary is equal to 0. So as you can see, this term is not there. So one way to prove it is to delete this term. And how can we delete this term? Well, we can take the scalar product with v, because this is v cross rotational of v. So that's in orthogonal direction to the v. So if we take the scalar product with v, we will therefore end up with something which is orthogonal. So then it would be 0, because the two vectors would be orthogonal to each other. Namely, that thing here is orthogonal to v. So if we take the scalar product with v, that's 0, obviously. So here we just have, right, it's straight. So now we have the scalar product dvdt with v minus 0. The gradient is there, and scalar product with v. So I just took the scalar product, that part here with v, right? All right, so the next step then, since this equation, the identity is an integral, so the Euler's equation is an equation which is valid for a element of the fluid. And that's obvious because V and all the functions, whole, everything, it's a function of the x, right? X and t. So they are valid for an element. So if we want to take in consideration all the fluid or all the whatever we want to take a bigger element, we need to integrate. So then we integrate what we had before on the V, where V is the volume. So V there, both sides. Integral dV, and I just passed the whole to the other side because who is a constant, so I pass to this side here. And now we are closer to what the question is asking, because now we just need to change the V integration to the boundary of V, or the superficial area, so an element of area. And then we know that we can do that quite easily. Right, so then we already have that integral. And basically, I'm just rewriting out this integral because I have here the gradient of a function, and that function is exactly h, because the question said h is whole v squared over 2 plus p plus whole phi. Right, so I just changed the name. This is just a whole, so just h, or just h. And I'm just repeating that line is equal to that line. Everything is the same. And now I need to know how I can deal with this term in order to get a surface integral, right? And then comes some more than one to at least three ideas which are very important here to finish that question. So the first one is we don't have the divergence, right? So you may remember that when we have the divergence, like here, in that case we have the divergence of a vector, let's say E, and by the Gauss theorem, which is similar to the Gauss law in physics, that's integration on V will be given by the integration on the boundary of V of that vector times the vector area vector, is ds vector, which is a vector orthogonal to the plane of the element of area. And basically it is because it's a vector, it has a direction, and that direction is direction n, is a unit vector, and it is a modulus, because as you know, this vector areas, they have modulus which is given by the area. So this area is given by that thing here, ds, element of area. So we don't have the divergent, but if you see that actually what we have here, we have the divergent of something times v. So the gradient, yes, the gradient of h times v. That's it. So that can be rewritten if we remember, if we have the total divergence of a function multiplied by a vector, that is equal to it's like the Leibniz rule for the multivariable calculus. So it's the gradient of the function scalar with v plus the function times the divergence of the vector. So we can change that bit here by that and minus that, right? So that's good. The other thing is we are doing that because we have in mind that we want to use that thing here. So we need a divergence, total divergence. So therefore it's here, all right, we found it. But the extra problem here, which is not a problem, is that we need this term here as well, right? So because of it's here, it turns out that this term is equal to, so it's equal to 0. And that's easy to see because we need to remember the continuity equation. So the continuity equation says that the ddt of the whole plus the divergence of the v is equal to 0. So if your whole is constant, that means that your whole does not depend on anything. So in particular, it doesn't depend on the time. So the derivative here is 0, right? So that thing here means that this is 0 as well. So that thing here, it's 0 as well, because this is 0. Then it made easier, because then we don't need to work with that term anymore. The term is not there. So basically we can just exchange that bit by that bit. And then because we use the continuity equation, right? And then we use the Gauss law here. And basically now what we have is easy, because now we have the ddt of that thing here, which is the velocity kinetical energy. It is, if we pass this to the other side, this minus becomes a plus. Here's a plus. Instead of the divergence, right, of h times v, we will use the Gauss law or the Gauss theorem, and actually we will use, instead of that, we will use the divergence of hv. But then this is like our E, like GZ here. So basically what's there is a plus. So we have d dt of that integral there on V, right, of whole V squared over 2 dV, plus, because we just changed the side, we use the Gauss theorem, so then this is on the boundary. And actually I'm going to write just one step before, so that step before is just plus the integral of V of the divergence of HV and dV. And from this line to that line, it's basically using Gauss. And you can just to confirm that that's true, just remember that when we use the Gauss theorem here, we need to take the scalar product of the vector, which is inside the divergence, with the area, vector area. And this vector area has n, which is here, and this s outside, which is here, right? So then that's proof, it's finished here, because that's exactly what the question asked us to show. That's equal to 0. As you can see here, that's equal to 0. And our final comment here is that this is called transportable energy. It can be transportable energy because we have ddt, so it is the time variation of the sum over the kinetical energy of the fluid. So that plus something else is equal to 0. So that is pretty much what is written in terms of continuity equation. As you can see here, we have d dt of whole, so a density of something, plus the divergence of something, and this is equal to 0, which is basically that thing here. So it's a continuity equation for something else, because here's the continuity equation for whole. So here is a kind of continuity equation for the energy density. So because of that is the variation of the kinetical energy, that term here, H, is the transportable energy. So it means that this energy is passing through. We have a volume, and this energy is coming in or coming out of that element of volume through the surface of this volume. And that's related, although it's and it can be understood as an energy. This H is related with this Bernoulli, because we know that the Bernoulli gives this as a constant along some lines, F lines, for example. And then the next question would be, for example, to understand the Bernoulli's principle, which is based on these Euler's equations as well. And that's it.